All right, hello geometry students. These will be the final notes leading up to the Unit 5 test, which will be on Thursday. So our final topic of discussion is special segments in triangles. Our objective for Tuesday's class is the student will acquire new vocabulary and properties for special segments in triangles. Again, these are the anticipated notes for Thursday, November the 19th. Please copy your objective and your date. As always, press pause anytime you need more time to copy something down, and then press play when you're ready to move on. Okay, now we're going to get into some new vocabulary here. Some of these words you have heard before. Maybe you even know the correct mathematical definition for some of these words, but some of these words are going to be different from the definition that you might have in the English language. So let's see what they mean in the mathematical language. Now here's a word we should all be familiar with. It is altitude. Now in the English-speaking world, altitude simply means height, like up off of the planet. Okay, like planes fly at a certain altitude. But in geometry, it does not mean that at all. An altitude of a triangle connects a side of the triangle to the vertex across from it, such that the intersection with the side is perpendicular. Now, it's a little bit of a wordy definition. Unfortunately, all those words are needed, as is the possible note that I have there, that altitudes do not necessarily have to be inside of a triangle. Okay, now just like always, I'm going to give you a couple of diagrams to go along with this definition. And here they are. I've given you two diagrams here. The left-hand one showing you an altitude that would be inside of a triangle, and the one on the right is an altitude that would be outside of the triangle. Now, in both cases, okay, they're both triangle ABC. Okay, line segment AD is going to be an altitude of these triangles, and it is an altitude because of what the definition says. It connects a vertex, in both of these cases, that would be vertex A, to the side across from it in such a way that it forms a right angle with the side that it is connecting with. Now on the left-hand side, left-hand diagram, obviously, it's connecting with line segment BC. Now, in the other triangle over on the right-hand side, it cannot actually connect to line segment BC because staying inside of the triangle to get over there to line segment BC, obviously it would not form a right angle by the time line segment AD actually got all the way over there. However, we can imaginarily or artificially extend line segment BC so that when line segment AD does connect, it can connect, forming a right angle. Now, also keep in mind, okay, these triangles do not necessarily have to be sitting in the position that they are sitting in. So we could take triangle ABC, we could rotate it, turn it over on its points, or different sides or vertices facing up or down or left or right. It would not have any difference. So do not fall into the trap of thinking altitudes are always perfectly straight up and down. They might be, but they might not be. The fact is they fit the definition. It connects a point to the side across from it such that a right angle is formed. That is an altitude. Okay, the next definition that we're looking at is going to be a median. Okay, now you're probably familiar with the word median a little bit from your days back in pre-algebra. Okay, a median was a number that was in the middle. Okay, and that's not true today, but there's a part of that definition that's going to remain true. A median of a triangle connects a side of the triangle to the vertex across from it such that the side is bisected. Now this is somewhat similar to the definition of an altitude. We are connecting a vertex to a side across from it. only this time we are not interested in trying to form a right angle with the side we are intersecting. We're simply trying to bisect the side. We want to make contact, just like with the word median you've learned before. We want to make contact in the middle. Okay, median does mean middle. Okay, so here is a possible diagram of a median in triangle ABC. Line segment AD would be said to be a median of triangle ABC. And again, simply because it follows the definition. It is connecting a point to the side that is across from it such that the side is bisected. And we can tell that it's bisected because of the tick marks that are in there. Okay. Now, once again, keep in mind the triangle can be twisted and turned and rotated and all kinds of stuff. Okay, a median does not necessarily come from the top vertex, like vertex A in this case, down to the side that happens to be on the bottom. Okay, median can be going anywhere as long as it fits the definition, connects a point to the side that's across from it, such that the side is bisected. Okay, this next one is a term that we are familiar with already. Okay, but let's go ahead and write it down anyway. It's been a while. Okay, an angle bisector. An angle bisector obviously splits an angle exactly in half. Okay, so here is triangle ABC once again, and this time we have an angle bisector positioned in it. We can see that the angle near vertex B has been cut exactly in half by ray BD because of the angle congruency marks that are in there. They each have one angle congruency mark, so the angle has been bisected. And as you know from our discussions a few months back about bisecting and the topic of bisected and midpoints and all that kind of stuff, there's a lot of different ways that this statement can be made. Ray BD bisects angle ABC. That is true. Angle ABC is bisected by ray BD. That is true. Angle BD is a bisector of angle ABC. That is true. That's one of the things that makes the English language so complicated, is that there are so many different ways of saying exactly the same thing. Okay. And again, it does not matter what position this triangle happens to be sitting in. Being an angle bisector simply means that we are bisecting an angle. It does not mean that it has to be on the left and the bisector has to be going horizontally. Certainly not anything like that. One more term that we have on special segments is what's called a perpendicular bisector. Now you can probably figure this out from the name. If a bisector happens to be perpendicular to the object it is bisecting, then we call that a perpendicular bisector. Now, a diagram that would go along with a perpendicular bisector might be something like this. Okay, we can see in this triangle ABC that we have a line segment ED that is participating in the diagram in some manner. Okay. And by the tick marks, we can see that line segment ED has bisected line segment AB. And by the right angle marker, then obviously it did it in such a way that they are perpendicular to each other. That's where we would get a term perpendicular bisector. This one's not real rocket science. If you have followed your vocabulary at all this year, you probably could have guessed this one on your own. And once again, for the fourth time, that has nothing to do with the positioning of the triangle. We could take the triangle, rotate it, reflect it, do all kinds of stuff to it. Okay, does not mean that a perpendicular bisector is going to be vertical in the picture. Doesn't mean that it's going to hit the side that is at the bottom of the diagram. They can be going anywhere as long as the conditions for being perpendicular and the conditions for being a bisector are both met. Now, I want you to consider, okay, a few things here. Okay, you can stop taking notes here for the next moment or two. I'll tell you when you need to begin again. If we were to apply each of these special segments to an isosceles triangle, here is what you would see. Now, all I've done here is I generated an isosceles triangle, this blue guy, and I copied it 3 more times and put them down. Okay, now I positioned all of these terms, the altitude on the left, the median at the left center, the angle bisector at the right center, and the perpendicular bisector at the right hand side. Okay, all of these are positioned exactly according to where their definitions say they should be, even to scale. Okay, so that altitude is exactly where it's supposed to be. Okay, so that it can form a right angle with the side that it's connecting to. The median is connecting exactly where it's supposed to be so that that side can be bisected. The angle bisector is positioned exactly where it's supposed to be so that the angle is cut exactly in half. And the perpendicular bisector, I actually left a marker too out of my perpendicular bisector. Well, no, I didn't. I've got it being bisected down at the bottom, and it is perpendicular. Okay, so all of these diagrams are drawn to scale. Okay, now the question or the point that I'd like you to consider as you are not taking your notes at this moment, I want you to just think about this. Do you notice anything in particular about these red line segments that I just installed into all four of these isosceles triangles? Well, hopefully by looking at it, you have some suspicion that it might be the exact same line segment. Okay, but maybe it's not. Maybe it's slightly off in some of these cases, and you simply cannot tell by eyeballing it. After all, there's been plenty of things that in geometry we've not been allowed just eyeball. Maybe it's difficult to tell. Okay, so what I did is I actually did a copy of all four of these triangles, including the red special segments that are in the triangle. I copied them and I placed them all on the same screen directly on top of each other. Okay, so this is all four triangles laying directly on top of each other. And what do you see? Obviously, we see the isosceles triangle. We see the different properties for the different special segments that we've talked about. But the thing I'd like you to notice in particular is the line segment down the middle. Can you tell the difference between any of the four line segments that's coming down the middle? No, you cannot. Okay, so here's where you need to start taking notes again. There's an important lesson in that. You need to copy this statement. Okay? In an isosceles triangle, the altitude, the median, the angle bisector, and a perpendicular bisector are all exactly the same line segment. And what that means is if you have any one of these four properties or these four special segments, any one of them, okay, then that will mean that you actually have all four of them and all of the properties from all four of them apply. Okay. Now, if you get to thinking about that, what that's going to mean to you is a problem may come along and say, hey, here's an isosceles triangle, here's a median in that triangle, and then start asking you questions about the altitude. Okay, so they may give you one of them, but question you about another one. It'll be up to you to know that when you have one of them in an isosceles triangle, then that is actually all four of them, and all four sets of properties actually apply. Okay, so that's a little bit of a strange property. Okay, but they love to ask questions about the strange properties that are out there. Okay, so let's move on. Let's take this one step further and look at the shortcut postulates about triangles we discussed a few lessons ago. Okay, you don't necessarily need to copy this one down either. Okay, but definitely follow along. Okay, let's see, using this triangle from the previous slide, let's see if we have enough information to show if all of our corresponding angles are congruent. Okay. Well, I think it's pretty obvious that we have one set of corresponding angles congruent right up there. Okay. Very also easily determined that we have a right angle right there, okay, because of the linear pair that exists here. Okay, so a right angle there, so we have two corresponding angles congruent. What about the third set of angles? Do we have enough information to figure out the third set of angles here and here? Yeah, we do. Okay, we have two angles in a triangle. We know that the three angles in a triangle are going to add together to equal 180 degrees. Okay, so that is enough. We will be able to find that all three sets are congruent. Okay, and we could say that yes, Those two triangles are congruent. Oh, I'm sorry. We're not trying to give it an example. We're just trying to say, yes, we do have enough information to say that all sets of corresponding angles are congruent. Okay. Next, do we have enough information to say that all corresponding sides are congruent? Well, obviously, we have the one set of tick marks there, so there's one set of sides. We have the matching set of two tick marks there, two sets congruent. What about the third set of sides? Now, the third set of sides is actually this guy that comes right down the middle, and it is in common for both of the triangles. So yes, we could say that we have all three sets of corresponding sides congruent. All right. Could we say we have congruence by side, side, side? Side, side, side. Similarity postulate says that if all three sets of corresponding sides are congruent, then you can say that the triangles are congruent by side, side, side. So yes, we do. Do you have enough information to say congruence by side, angle, side? Okay. Well, this one actually you do in a lot of different places. We've already established that this side coming down the middle there on that special segment is congruent because it's in common with both triangles. Okay, so we could like pick on this guy up near vertex A. We have a set of sides congruent, then we have an angle that is congruent, then we have another set of sides. So you have side, angle, side, side, angle, side. Okay, so we actually could do that on any of the angles or any of the sides and angles for side, angle, side in this particular picture. Just happen to use the one up at the top. Do you have enough information to prove congruence by angle, side, angle? Yeah, well, coming right down the special segment, that would be pretty easy. Again, we know that this side is congruent to itself. So you have a set of angles right there, then a set of sides, then another set of angles. Angle, side, angle. And same thing over here. Angle, side, angle. Okay, and we could pull this off at some of the different vertices as well. But yes, we do definitely have enough information to say they are congruent by angle, side, angle. How about congruence by angle, angle, side? Okay, well, let's see what we have. We have a set of angles right there that are congruent. If we travel along, we have at the very next intersection, we have another set that are congruent right there. And then we have a set of sides. Angle, angle, side, angle, angle, side. So yep, we could do that, and that is not the only place in the diagram where we could have pulled that one off either. I think you're getting the message here. Do you have enough information to prove that you have congruence by side-side angle? Well, if you've kind of let your brain go to sleep, you would probably say, yep, we've got enough information to say I've got a set of sides congruent, and then another set of sides congruent, then another set of angles congruent. But what was that one we said absolutely we watch out for? No such thing as angle, side, side. And again, it's not because we don't like the word that it spells when it's in reverse order or anything like that. It is simply because having a set of sides congruent, then a set of sides congruent, then a set of angles congruent, or a set of angles, then a set of sides, then a set of sides, that does not actually force the two triangles to be congruent. So watch out for that one. Okay, but again, you can see how many properties they are when a problem wants to bring an isosceles triangle into the picture. There is a lot of information going on in there. Now, there's one other type of special segment that we might see. Okay, so I'm going to bring this one to your attention as well. This one is not as well known, but it has been showing up in recent years, so we're going to take a look at it. Okay. If you were to take a triangle of any kind, this one isn't necessarily just isosceles, but a triangle of any kind, and connect the midpoints of two sides of a figure, okay, then that line segment connecting those two midpoints is what we call a midsegment. For those of you that have tuned me out, this is where you would want to be taking notes again. This is a new definition. Okay, so as you can see, coming down the left side of that triangle, we've got a matching set of 1 tick marks. Coming down the right side, matching set of 2 tick marks. So the 2 red points on either side of the triangle are midpoints, and they are connected with that green line segment. Okay, and the only real property that we have for a mid-segment is that a mid-segment is always going to be parallel to one of the sides of the triangle. That's an important piece of information. Okay, when a problem brings a mid-segment into the picture, okay, that causes parallel lines, and wherever you have parallel lines, we have all of those rules for parallel lines and transversals. We got alternate interior angles, corresponding angles, all that kind of stuff comes back into play. So you can see in geometry how that old information just keeps on coming back and coming back and coming back. Okay, so that's the final definition. I have an example here that I am going to allow you to tackle in your notes. Then we will cover it in class on Tuesday. Okay, now it looks very complicated. There's a lot of information going on inside of this diagram, and obviously there's several variables that will need to be discovered. Okay, but I want you to take it just a step at a time. In triangle JKL, line segment LJ is congruent to line segment KL. If I were you, I would find that in the picture after I got it copied down and find a way to mark it. Also, line segment LM is an altitude. I would look up the definition for altitude, find out what that means to the picture, and mark it. Line segment MN is a median. I would look up that definition, find out what that means to the picture, and mark it. Based upon that information, you ought to start to be able to see what kind of relationship is going on around the X, what kind of relationship is going on around the Y, what kind of relationship is going on around the Z. Should be able to get an idea on how to work some of these problems, how to set them up, and how to solve for them. So have a look at this diagram and see if you can solve for X and Y and Z. And I will see you in class tomorrow. If you need more time to copy down the diagram, go ahead and press pause now before the video ends. And I appreciate you finding time to do your notes.